Hello everybody. Today we are going to go over kind of a crash course, brief review of all the basics of Chemistry 1. Before we begin this video, I would advise you that in order for this to make the most sense, you're going to need a periodic table in your visible area. If you don't have a periodic table where you can see it right now, I would pause this video and go get one because it's going to make everything else make a lot more sense. All right. So with that in mind, we are going to start by discussing the modern periodic table. The modern periodic table is arranged in order of increasing atomic number. This was an arrangement that was developed by Harry Moseley, and this is really useful because atomic number is something that is unique for every element. No two elements can have the same atomic number. I do want to throw in there as a review, though, that this was not the first modern periodic table arrangement. The first modern periodic table was developed by Dmitri Mendeleev, you might remember, and he arranged his periodic table by atomic mass. Although atomic mass is a pretty good fit and the majority of elements will fall in the right place based on atomic mass, it's not ideal because there can be multiple elements that have the same or very similar atomic masses, and the atomic mass can vary for isotopes of the same element. All right, so let's take a look at a block that you might see on the periodic table. So I have drawn in a block for nickel. Things that you will commonly find on each block of the periodic table. You're going to find in the center, usually, the chemical symbol. Please keep in mind that when you write chemical symbols, they're either one-letter or two-letter symbols. If it's a one-letter symbol, it's a capital letter first. If it's a two-letter symbol, then it's capital letter followed by lowercase letter. As you type in answers or handwrite answers, please be very cognizant of that and write neatly so that I know what you mean. All right, then usually in the top right or along the top of the box, you are going to find a whole number. In this case, for nickel, you will find 28. That number tells you the atomic number. And remember, the atomic number is equal to the number of protons. You will also frequently find a number at the bottom of each box on the periodic table. It typically will be a decimal because this is the average atomic mass for that element. Because it's an average of the different masses of the isotopes, that's where the decimal comes from. It's loosely based upon the number of protons plus the number of neutrons, which is the mass number, and we'll talk about that here in a little bit. All right, I've sketched in a very crude periodic table. I'm definitely not an artist, but this gives us kind of the basics of a periodic table. A period, I want to remind you, is a horizontal row, so that means left to right. Elements that are in the same period are in similar energy levels for their valence or outermost electrons. The mass will increase as you go from the left to the right within a period. The other main arrangement that we should review is a group or a family. Groups are the vertical columns on the periodic tables. They are called families because they have similar properties. Why do they have similar properties? Because all of the elements in a group or family will have the same number of valence electrons. Now remember, valence electrons are the outermost electrons, and those are the ones that you gain, lose, and share when you are forming chemical bonds. I have gone through on my skeletal periodic table up here, and I have written the number of valence electrons at the top of each family. So the furthest left column has 1 valence electron, as you can see here. Then the second has 2. Remember, we skip this middle block here, the transition metals, because that's also the D block. And if you remember, D electrons are always 1 energy level below, like this first row of the transition metals, even though I didn't draw it properly, I apologize, is actually the 3D shell, but it's in the 4th row of the periodic table. So we just skip over those. We go over to boron's family, and they would have 3 valence electrons. Carbon's family would have 4. Nitrogen's family has 5. Oxygen's family has 6. Fluorine's family has 7. And then the noble gases have 8 valence electrons. All right, with that in mind, saying that those are the noble gases, we should go over the names of these families. So the column that I have in pink, the first group here, is often called the alkali metals. The alkali metals include lithium, sodium, potassium, rubidium, cesium, francium. They are by far the most reactive of the metals, especially when they are exposed to water. These are the ones that will burst into flame just by coming in contact with water vapor in the air, in the atmosphere. So you have to be very careful, seal them and store them where they are surrounded by oil, because oil doesn't like water. And so it won't let the water vapor around the metal sample. The column 2, I have shaded in green. They are known as the alkaline earth metals, and they have similar properties. So this is beryllium, magnesium, calcium, strontium, barium, radium. These elements, although they will react with water, it has to be pretty hot water, and it won't be nearly as violently reacting. We will frequently use samples of magnesium in lab, and they're not considered dangerous or explosive. Remember, magnesium ribbon's the one that will burn very bright white when you expose it to flame. Now we're going to skip over here to the blue column, group 7 or group 7A, group 17. Those are the halogens. So these are like fluorine, chlorine, bromine, iodine. These are the most reactive of the nonmetals. And then the orange group here is the noble gases, and the noble gases are like what all of the other elements are trying to become like, because they have a full set of 8 valence electrons. They satisfy that octet rule, you might remember. So they are the most stable. Another term that we used to mean stable is inert. So if you hear the word inert, that means that it's not going to react with anything. And then we've already discussed that the center part that I have shaded in yellow is where the transition metals live. A brief review, which we'll get into this later on this semester as a review, but the transition metals are the ones that have the Roman numerals associated with their names, because they have varying amounts of valence electrons and can make +2, +3, +4 different forms of the same metals ions. Other important categories for you to review: we can group elements as metals, nonmetals, and semimetals. Metals are found on the left side of the periodic table. I will say that the vast majority of elements are considered to be metals. That's the most popular category. They are malleable, which means if you strike them, they will bend without shattering. They can be hammered into thin sheets or foil, which is very useful. They're ductile, which means that they can be drawn into wires. They're shiny, and they are good conductors of heat and electricity. The vast majority of metals are solids at room temperature. Remember, there is one metal that is a liquid at room temperature. That is mercury. The nonmetals can be found on the right side of the periodic table, and essentially they're like the opposites of metals. They are brittle, which means if you strike them, they will shatter. They are poor conductors. Sometimes instead of saying poor conductors, we'll call that being an insulator. Some of them are gases at room temperature, some of them are solids. There is one liquid nonmetal at room temperature, that is bromine. Then the third category is the semimetals, which can also be known as the metalloids. These share properties of both metals and nonmetals. They tend to be shiny and look like a metal, but they are very brittle when you strike them. They can be conductors of an electric current when the temperature and conditions are right. I am gonna kind of put some purple here, because if we go back up to my skeletal periodic table, I have kind of drawn in this purple stair step, which is where the semimetals are located, and they kind of form the borderline between the metals on the left side and the nonmetals on the right side. All right. The next thing that I like to review with my students is subatomic particles. These are the things that are smaller than an atom, that are found in different combinations inside of every atom. The first subatomic particle we should review is electrons. Electrons have the symbol E negative because they have a negative charge. They are so tiny that we consider their mass to be 0 AMU. Remember, AMU is a unit that we use in chemistry that stands for atomic mass units, because kilograms and other units that we frequently use are just way too large for dealing with these particles. We had to develop a new unit to work with. Electrons can be found in the electron cloud or orbitals. Basically, they're outside of the nucleus. Protons are the second type of subatomic particles. We give protons the symbol P positive because they are positive in charge. They have a mass of 1 AMU and they are located inside the nucleus. Neutrons are neutral, so they have the symbol N0 or N0. They have a mass of 1 AMU and they are found inside of the nucleus. We've already discussed this today, but just another reiteration of this. The atomic number is equal to the number of protons inside the atom, and it's unique for every element, always a whole number. Mass number is equal to the number of neutrons plus the number of protons. There can be isotopes of the same element, so that means if they're the same element, they've got to have the same number of protons or the same atomic number, but they can have different numbers of neutrons. I do want to throw out there that, remember, to find the number of neutrons, you can use the acronym MAN. You take the mass number minus the atomic number, and that will tell you how many neutrons you have inside of your atom. Another point that we should discuss is when the number of protons equal the number of electrons, that means your positives and your negatives balance, so you have a neutral atom. When the number of protons does not equal the number of electrons, you're going to have an ion. There are two different categories of ions. When the protons, when you have more protons than you do electrons, that means you're heavy on the positive charge, and we call those cations. When the number of protons is less than the number of electrons, that means you've got more negatives, so you will have a negative anion for your ion. Let's review briefly some different ways to describe or denote the atom that you are working with. Let me choose a different color here. So if I gave you the hyphen notation, nitrogen 15, this number that's at the end of the hyphen always tells you the mass number. And remember, we just said that the mass number is equal to the number of protons plus the number of neutrons. So I have to go to the periodic table, look up nitrogen. The symbol for nitrogen is a capital N. Find it on the periodic table and look at what number is at the top of the box. At the top of its box is a 7, which tells me that I have 7 protons. This is not an ion because they don't call it nitrogen ion. They don't call it nitride. So that indicates to me that this must be neutral. And in order for it to be neutral, there have to be an equal number of protons and electrons. So I'm going to say there's 7 electrons here. To find my neutrons, remember I've got to use that MAN prefix. I take my mass number of 15 minus my atomic number of 7, and that gives me 8 neutrons overall. So what about if we flip this around and I tell you that you have 5 protons. Oops, I didn't mean to put electrons there. Let me erase that. Let's put that you have, whoops, fix my mistake. Let's say that you have 4 neutrons, and I want you to give me the hyphen notation. So I'm going to have to go to the periodic table and look up what element has 5 protons. When I look that up, I see that there's a symbol of capital B. Capital B is the element boron, so I put boron, and then I'm going to put hyphen mass number. Well, the mass number is the protons plus the neutrons, so 5 plus 4 is 9. The correct hyphen notation is boron-9. Another way of representing your elements is by using a complete nuclear nuclide symbol. It kind of depends on which book you're using, whether they're going to call it a nuclear or nuclide symbol. So in a complete nuclear symbol, you're going to have several different parts. In the center, you are going to have the symbol for the element. So in this case, I have a capital V, which tells me that I'm working with vanadium. It's not asked of me, but I do want to clarify that that's what that V stands for. This number down here in the bottom left, in this case it's a 23. That tells me the atomic number. This number 50 in the top left is where you will find the mass number. And this +4 over here is indicating to me that we have a charge, a +4. So I am asked to tell how many protons, neutrons, and electrons are in this particular nuclide or atom, ion, particle, I guess I should say. So if I look, the number of protons is equal to the atomic number. We said the atomic number is this number down here. So that means I've got 23 protons. Neutrons, I find neutrons by taking my mass number minus my atomic number. So 50 minus 23 gives me 27. Now, electrons, I cannot assume that because there's 23 protons, there's also 23 electrons, because in this case I have a charge. The charge is telling me that I have an overall positive charge, so that means I've got more protons than I do electrons. If I had 23 protons and I know that there's a 4+ charge, that means there's 4 more protons than there are electrons. So if I take 23 minus 4, that tells me that I've got 19 electrons. Essentially what you'll always do to find the electrons on an ion, you'll take the number of protons, because that cannot change, and you'll do the opposite of what the charge says. So like 23, I had to take away 4 to find my electrons here. If this was a -4, I'd take 23 and add 4. The last thing that we want to review is empirical versus molecular formula. Empirical formulas are when the formula is in the simplest form. There can be several molecules that share a common empirical formula. Molecular formulas are not necessarily reduced. So let me give you an example. If I had C6H18, let's say, that right there is a molecule. Because 6 and 8, the ratio of 6 to 8 is not in lowest form, because both 6 and 18, I apologize. 6 and 18 is not in simplest form, because 6 and 18 are both divisible by 6. This would be a molecular formula. If I was asked to turn it into an empirical formula, I would have to reduce it and basically divide each of those numbers by the common divisor. So 6 divided by 6 is going to give me 1, and 18 divided by 6 is going to give me 3. So the empirical formula for this molecule would be CH3. So molecular formulas are not necessarily in simplest form, and empirical formulas have been reduced to their simplest form. I hope this helps you to better understand the concepts of Chemistry 1 and to complete today's assignment.